In this video, I will walk you through free response question number 2 from AP Calculus Practice Exam 1. This problem is primarily about area and volume. This problem is considered calculator active, so we will use our graphing calculator as needed. If you have not yet watched free response question number 1, you should probably watch that first. You can either click the link in the upper right hand corner or find the link in the description. Let R be the region in the first quadrant bounded by the x-axis and the graphs of y equals natural log x and y equals 5 minus x, as shown in the figure above. Part A. Find the area of R. If you integrate with respect to x, you can find the area between two curves by integrating the top function minus the bottom function. For this problem, we will have to write two separate integrals and add them together because the top function changes from the red function, natural log x, to the blue function, 5 minus x. But first, we need to find the x-coordinate of the intersection between the two. Let's type both of these equations into our graphing calculator and find this intersection point. Hit y equals and type in your equations. Notice that I have typed natural log x in as y2 and 5 minus x as y3. I also put y equals 0 for the x-axis on y4. Before we hit the graph button, let's adjust the window. We are only interested in the first quadrant, so let's let x min equal 0, and let's let y min also equal 0. Now hit graph and take a look. So this is the zone that we are trying to find the area of. We need to find the x value of this intersection point, so hit second trace and choose option 5 for intersection. Move the pointer close to this point of intersection, and I want to say hit enter 3 times, but be careful that we are only dealing with the magenta function and the red function. So I'm going to hit enter, and now I've got the magenta, enter, and enter again. So this is the x-coordinate of the intersection point. I want to store this into a letter for future use. So quit your way out and hit the X button and then the store button. I'm going to store this into letter A. So alpha A, enter. This way, if I need this value again later, I can just type A. Otherwise, I have to type in all of these decimals. Record the value of A somewhere in your work as well. So let's write an integral expression for the area of the yellow region. That will be the integral from 1 to A. And next we will have top minus bottom. On top it is natural log x, and on the bottom it is 0, which we don't really need to write. Next we add an expression for the blue area, which will be the integral from A to 5. And again, I'm thinking top function minus bottom function. So that is 5 minus x minus 0, but I don't need to write a minus 0. Now we can type this whole expression into the calculator to find the area. So let's see, the integral from 1 to A of natural log x comes first. For the integral, we do math 9, and we want the integral from 1 to A, and we can just use A. If you did not store this number in A, right now you need to type in this entire number with all the decimals. I recommend doing it this way. And here we have the natural log of x, so there you go. Now we need to add the second integral, which is the integral from A to 5 of 5 minus x. So math 9, A to 5, 5 minus x. Kabam! 2.986 if you round, or 2.985 if you truncate. Part B. Region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. When they say region R is the base of a solid, I want you to picture an oddly shaped loaf of bread that is sitting on region R. We are looking down at the top of the loaf from above. We can find the volume of the solid by adding or integrating slices. It's a three-step process. Step 1 is to find an expression for the length of the base of a single slice. Step 2 is to find an expression for the area of a single slice. And step 3 is to find the volume of the solid. Let's start with step 1. So first we need to find an expression for the length of the base of a single slice. However, the expression will be different depending on whether we are in the yellow side of region R or the blue side. So we are going to have to write two different expressions. Basically, we will find the volume of the yellow side and the volume of the blue side separately and then add them together. So let's start with the yellow side. A random slice perpendicular to the x-axis might look like this. Imagine that this blue segment represents the length of the base of this slice. This length can be found by subtracting the top function minus the bottom function. The top function is natural log x, and the bottom function is 0, and we don't really need to write the 0. So this is an expression for the length of the base of a single slice in the yellow area. How about the blue area? Let this blue segment represent the length of the base of a single slice in the blue area. We can find this length by subtracting the top function minus the bottom function. The top function is 5 minus x. And the bottom function is 0, but again, we don't need to write that. Step 2 is to form an expression for the area of a single slice. In the setup, we are told that each cross-section perpendicular to the x-axis is a square. A cross-section is a slice. So they are saying that each slice is a square. If we pulled out a slice and looked at it, it might look like this. This would be the base of the slice that we just found an expression for. For now, let's call it B. If the base of this slice is B, what would be an expression for the area? Well, since it is a square, the area will simply be B squared. They were very nice to us on this problem, and they gave us slices in the shape of a square. So if the base is B, then the area is B squared. But here are some other types of slices that often show up on the AP exam. Sometimes the slices are in the shape of a rectangle, and of course the area will be base times height. Here are some other formulas that I want you to go ahead and memorize. If the slices are in the shape of an isosceles right triangle, where one leg of the triangle is the base, then the area of a single slice will be 1/2 b squared. That's sort of common sense because it's just half of a square, so 1/2 b squared. If the hypotenuse of the isosceles right triangle is the base, then the area is 1/4 b squared. And you can sort of picture that in this configuration, a single triangle is 1/4 of a square, so that's why it's 1/4 b squared. These last two you simply have to memorize. If each slice is an equilateral triangle with base b, then the area of a slice is radical 3/4 b squared. If each slice is a semicircle with base b, then the area of a slice is pi/8 b squared. Notice that all of these have b squared in it, so all you really have to do is memorize the coefficient of each one. Anyway, back to the easy one. Each slice is a square, so the area will be b squared, the base squared. Since we have an expression for the length of the base, if I want to turn this into an expression for the area of the slice, I need to take the base and square it. So if I just go like this, kabam! Now this is an expression of the area of a slice, at least in the yellow region. In the blue region, same deal. Take the base and square it. Now we have an expression for the area. So that was step 2. Finally, we can find the volume of the solid by integrating the area of a single slice. Integration is actually addition. That's why the integral sign is an S. It stands for sum. So when we integrate the area of a single slice, we are actually adding up all of the slices, in this case from left to right, in order to form the solid. So we are going to find the volume of the yellow part of the solid by integrating this area. These slices are stacked up between 1 and A. So on this side, we will integrate from 1 to A. And then for the blue part of the solid, we will integrate from A to 5, because these slices are stacked up between A and 5. This is an expression that we can type into the calculator. For the integral, we hit Math 9, and we are integrating from 1 to A. Because we need to square natural log x, I'm going to put some extra parentheses in here. And now I have natural log x, and I'm closing the parentheses so I can square it. And now here comes the second integral. So Math 9 again. This time we are integrating from A to 5. And again, because we are going to square an expression inside of here, I need an extra set of parentheses. So we have 5 minus x in here. Close the parentheses and square it. And that's it. Kabam! 2.784. So that's it for part B. Actually, the direction said to write but do not evaluate an expression. So just forget about that last part. Part C. The horizontal line y equals k divides R into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. Okay, so here is the horizontal line y equals k, splitting region R into two regions of equal area. So the yellow area is equal to the blue area. Our goal is to set up an equation involving one or more integrals that also has a k in it. To make the value of k show up in our integral, we will have to integrate with respect to y. So we can do things like the integral from 0 to k. In order to integrate with respect to y, we need to get x by itself. So I took the equation y equals natural log x and I flipped it around, and I put a base e on both sides. The e and the natural log cancel out, so I end up with x equals e to the y. On the linear side, I can just add x to both sides and subtract y from both sides, and I get x equals 5 minus y. So these are the two expressions I can use in my integral. If the blue area and the yellow area are equal, then the blue area should equal half of the total area. So let's start by writing an expression for the blue area. We can find the blue area by integrating the function on the right minus the function on the left. So that's 5 minus y minus e to the y. And we are integrating with respect to y. Notice that the blue area goes from 0 to k. So we will integrate from 0 to k. And this should equal 1/2 of the total area. Remember that we found the total area in part A. It was 2.986. And the directions say write, but do not solve an equation. So we can just stop right here. Let me emphasize one thing. The order in this expression does matter. If I wrote the e to the y first, the answer would be wrong. So that's it for part C.